Hello there, and welcome. If you have found your way here tonight, then perhaps you are the kind of person who likes to fall asleep thinking about something vast, something so large and so unhurried that the ordinary worries of the day simply cannot keep up. And if that is you, then what we are going to explore together this evening is worth a few unhurried sentences. Because tonight, we are going to talk about something that has quietly unsettled the world of astronomy for decades. Something that sits at the very heart of how we understand the cosmos. And it is this: the universe is hiding something from us. Not a little something, not some minor detail tucked away in a corner of a calculation somewhere. We are talking about 40% of all the visible matter that should exist in the entire observable universe. 40%. Gone. Invisible. Slipping past every telescope and detector we have ever built, as though it simply does not want to be found. And if that were not enough, the force that is driving our universe apart, the invisible engine behind the accelerating expansion of all of space itself, may not be behaving the way our models say it should. It may be weakening, slowly, quietly, but weakening nonetheless. And then there is a third puzzle, sitting alongside the other two, like a question that refuses to resolve itself, no matter how carefully you ask it. A number, a single measurement of how fast the universe is expanding right now. And depending on how you measure it, you get two different answers. Answers that should agree. Answers that simply do not. Three puzzles. Each one enormous on its own. Each one connected to the others in ways that scientists are only beginning to understand. So let us begin. Slowly. There is no rush tonight. The universe has been holding these secrets for 13.8 billion years. It can wait a little longer while we settle in and take them apart, gently, one by one. Oh, let us start with what we know. When astronomers point their telescopes at the sky and count everything they can see, every star, every cloud of gas, every grain of cosmic dust, every galaxy spinning slowly in the dark, and they add it all up, they arrive at a number. A truly staggering number. More than 100 sextillion kilograms of visible, ordinary matter. That is the number one, followed by 53 zeros. It is a number so large that it has almost no meaning to a human mind trying to hold it quietly before sleep. And yet, as enormous as that number is, it only represents about 5% of everything the universe contains. The rest is something else entirely. About 27% is thought to be dark matter, a substance that has mass, that exerts gravity, that shapes the movement of galaxies and the large-scale structure of the cosmos, but that does not interact with light in any way. It does not absorb it. It does not reflect it. It does not emit it. And so, to every telescope we have ever built, it is completely and perfectly invisible. The remaining 68% is stranger still. It is called dark energy, and rather than being a type of matter at all, it appears to be a property of space itself. A kind of pressure woven into the fabric of the universe, pushing everything apart, causing the expansion of space to accelerate rather than slow. It is the reason that distant galaxies are not just moving away from us, but moving away faster and faster with every passing billion years. So 95% of our universe is made of things we cannot see and do not fully understand. That is a remarkable thing to sit with. But here is where the story becomes particularly interesting for tonight. Of that remaining 5%, the visible, ordinary matter that we can in principle detect, about 40% of it is missing. Not dark matter, not dark energy, ordinary matter, the kind made of protons and neutrons and electrons, the kind that makes up stars and planets, and you and every breath of air you have ever taken. 40% of the ordinary matter that our best models say should exist in the universe today simply cannot be found. Now, you might reasonably ask how we know it is missing if we have never seen it. And that is exactly the right question. The answer comes from the very beginning of time. In the first few 100,000 years after the Big Bang, the universe was a hot, dense, glowing sea of matter and radiation. Light and particles were so tightly coupled together that the universe was essentially opaque, like the inside of a star. And then, as space expanded and things cooled, something remarkable happened. The universe became transparent. Electrons and protons combined to form the first hydrogen atoms. Light was finally free to travel. And that ancient light is still traveling today in every direction, filling all of space with a faint whisper of microwave radiation. This is called the cosmic microwave background. And it is, in a very real sense, a photograph of the universe as it was nearly 14 billion years ago. By studying it with extraordinary precision, cosmologists have been able to calculate exactly how much ordinary matter was created in the Big Bang. Not roughly, not approximately, to within a few percent. It gives us a precise budget, a firm accounting of how many atoms should exist in the universe today. And when astronomers go out and count every star, every cloud of gas, every wisp of plasma they can find, they only come up with about 60% of what should be there. For decades, this was one of cosmology's quiet embarrassments. The models were beautiful and well tested in so many other ways, but 40% of ordinary matter was simply not showing up. Scientists called it the missing baryonic matter problem. Baryonic being the technical name for ordinary matter, the kind made of the particles that make up atoms. Where was it hiding? The first clue came from an idea that had been quietly developing since the 1980s, when astronomers began mapping the distribution of galaxies across large regions of space. They noticed something extraordinary. Galaxies are not scattered randomly. They are arranged in a pattern, a vast, delicate, interconnected structure stretching across hundreds of millions of light years in every direction. A structure that looks, when you step back far enough to see it, something like a web. It has become known as the cosmic web. It is thought to have formed because the early universe was not perfectly smooth. There were tiny fluctuations in density, places where matter was ever so slightly more concentrated than average. You can see the fingerprints of these fluctuations in the cosmic microwave background, those faint ripples in the ancient light from nearly 14 billion years ago. Over time, gravity did what gravity always does. It amplified those tiny differences. Where there was slightly more matter was drawn in. Regions of higher density grew denser still, and regions of lower density grew emptier. Over hundreds of millions of years, this process shaped the universe into the structure we see today. Long filaments of matter stretching between dense nodes where galaxy clusters gather, and vast empty voids in between, hundreds of millions of light years across, containing almost nothing at all. The nodes of the cosmic web are the galaxy clusters, the dense intersections where the filaments meet, and it is along those filaments, in the vast stretching threads between the clusters, that scientists began to suspect the missing matter might be hiding, not in galaxies, not in stars, but in between, in long diffuse clouds of extremely hot, extremely low density gas, stretched along the filaments of the cosmic web like moisture along a spider's thread after rain. This gas has a name. It is called the warm, hot intergalactic medium, and the simulations have long suggested that it could account for a significant portion of the missing baryonic matter, perhaps most of it. The problem was finding it. The warm, hot intergalactic medium is extraordinarily difficult to detect. It is hot, certainly, millions of degrees in places, but it is also so diffuse, so thinly spread across such enormous distances, that the signal it produces is almost impossibly faint, like trying to hear a whisper across an ocean. For years, astronomers had hints. In 2005, NASA's Chandra X-ray Observatory captured images of two large intergalactic clouds of diffuse gas between distant galaxies. It was suggestive. It was promising. But the signal was too faint to isolate cleanly, and scientists could not say with confidence that this was the cosmic web revealing itself. Then in 2012, a combination of 18 Hubble Space Telescope images was used to infer the presence of a filament funneling matter into a distant galaxy cluster. Scientists found it not by seeing the gas directly, but by studying how the filament's dark matter warped the light from galaxies behind it. A gravitational shadow, indirect, tantalizing, but still not the thing itself. 2 years later, in 2014, a team led by Sebastiano Cantalupo at the University of California made something closer to a direct observation. They found an enormous filament of hydrogen gas, nearly 2 million light-years across, illuminated by a bright quasar shining on it from 10 billion light-years away. The quasar was acting like a cosmic flashlight, lighting up gas that would otherwise be invisible. And for the first time, part of the cosmic web had been seen directly. Using the same principle, astronomers in 2019 revealed whole networks of hydrogen filaments surrounding a massive protocluster, directly imaging the web on truly large scales. But there was a problem with all of these detections. They all depended on a cosmic flashlight, a bright nearby quasar to illuminate the gas. Without one, the filaments faded back into invisibility. And quasars are not scattered conveniently around every filament we might want to examine. To truly understand the cosmic web as it exists today in the local universe, without relying on chance illumination, a new approach was needed. In 2023, a team of astronomers at an observatory in Hawaii designed an instrument dedicated specifically to searching for the faint spectral signature of hydrogen gas in cosmic filaments. It detected the characteristic fingerprint of hydrogen as it absorbed and re-emitted radiation, a signal called Lyman alpha emission. And it worked, not just once. They began building three-dimensional maps of filaments, capturing their shape and extent in a way that had never been done before. And then, in January of 2025, the picture sharpened dramatically. Using an instrument called the Multi-Unit Spectroscopic Explorer, mounted on one of the world's largest ground-based telescopes at the European Southern Observatory in Chile, a team of international astronomers captured one of the clearest direct images yet of a cosmic filament. About 3 million light-years long, and using supercomputer simulations built on the data they collected, researchers were able to model a filament that matched the one they observed in the real universe. It was a remarkable achievement, but there was still a catch. These observations were tracing cool hydrogen gas in the distant early universe, billions of years in the past. The missing baryonic matter that our models predict should exist today in the local universe is thought to be much hotter. It is the warm, hot intergalactic medium, detecting it requires different methods, different instruments, and a great deal more patience. For a time, astronomers were stuck. And then, in June of 2025, something changed. A team of European researchers, led by an astronomer at Leiden University in the Netherlands, used a Japanese X-ray space telescope called Suzaku to map a single cosmic web filament in faint X-ray emissions, scanning it across a wide area of space with careful, painstaking observations. They then used a second telescope, the XMM Newton, to identify and remove sources of X-ray contamination, including the signals from supermassive black holes that would otherwise blur the picture. What remained, once all of that work was done, was extraordinary. A filament of the cosmic web, visible in X-ray light, connecting 4 galaxy clusters, 2 on each end, and between them, a band of glowing gas stretching across 23 million light-years of space. That is the equivalent of laying 230 Milky Way galaxies end to end. The filament has a mass roughly 10 times that of the entire Milky Way. Its gas glows at temperatures of around 10 million degrees Celsius, and its texture in the images, described as something like honeycomb or bone marrow, reveals in extraordinary detail how galaxy clusters are connected across distances that are almost too large to imagine. And according to one of the paper's co-authors, the filament looked exactly as their best large-scale cosmological simulations had predicted it would, after decades of searching, after hints and whispers and near misses, after all of the careful, patient work of generations of astronomers. The cosmic web had finally shown itself, and it matched the models. The missing baryonic matter had been hiding in the bones of the universe all along. But even as that discovery was settling into place, another question was quietly growing louder. And to understand it, we need to go back to 1998. At that point, scientists already knew that the universe was expanding. Edwin Hubble had demonstrated that nearly 70 years earlier by showing that distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. The universe was not static, it was growing, and it had been growing since the moment of the Big Bang. What scientists in the late 1990s were trying to work out was whether this expansion was slowing down. Logically, it seemed like it should be. Gravity, after all, is a force of attraction. Everything in the universe pulls on everything else. Over time, that collective pull should put the brakes on the expansion, causing it to decelerate. 2 independent teams of astronomers set out to measure this deceleration. They used a special kind of stellar explosion called a Type 1a supernova. These explosions are useful to astronomers because they always release roughly the same amount of energy. By comparing how bright they appear from Earth to how bright they should actually be, astronomers can calculate exactly how far away they are. And by measuring how much their light has been stretched during its journey through expanding space, what astronomers call redshift, they can figure out how fast the universe was expanding when that light was emitted. It was an elegant method, and when both teams applied it to more than 50 supernovae, they expected to confirm that the expansion of the universe was slowing. Instead, they found the opposite. The supernovae were dimmer than expected, not because there was something wrong with the method, but because they were farther away than they should have been, which meant the universe was not decelerating, it was accelerating. Space itself was expanding faster and faster. Something was pushing it apart with increasing force. This was one of the most unexpected discoveries in the history of science. The The three astronomers who led the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics for their work, and the force responsible for this acceleration was given a name: dark energy. Nobody knows what dark energy actually is. Most scientists think it is a property of the vacuum of space itself. That empty space is not truly empty, but carries some intrinsic energy that pushes outward against gravity. Others have suggested it might be a kind of field that fills the universe, or some subtle flaw in our understanding of gravity at the largest scales. But whatever it is, its discovery gave rise to a new model of cosmology, one that brought together everything we knew about dark matter, ordinary matter, and this newly discovered dark energy into a single coherent framework. It is called the lambda cold dark matter model. Lambda being the Greek letter that represents the cosmological constant, Einstein's original mathematical term for the energy of empty space. And it has been the standard model of cosmology ever since. Within this model, dark energy accounts for about 68% of the universe, dark matter for about 27%, and ordinary baryonic matter, all the stars and planets and gas and dust and everything we have ever touched or seen or imagined, just 5%. And crucially, within this model, dark energy is assumed to be constant. It does not change over time. It is woven permanently and unchangeably into the fabric of space, a fixed feature of the universe, like the speed of light or the charge of an electron. This constancy has enormous consequences. If dark energy is constant and the universe continues expanding forever, then the long-term future of the cosmos is already written. Over trillions of years, galaxies will drift apart as the space between them grows. Eventually, they will pass beyond each other's observable horizons, each one isolated in its own expanding bubble of space. Stars will burn through their fuel and fade. New stars will form more rarely, as the gas to make them grows thin. One by one, the lights of the universe will go out. Black holes will persist for a while, slowly evaporating through a quantum process called Hawking radiation. And eventually, after timescales so long that our current numbers have no adequate words for them, all that will remain is an infinite expanse of cold, dark, nearly empty space, barely above absolute zero. This is called the Big Freeze, and for nearly 3 decades, it has been the most likely predicted fate of our universe, or so we thought. In 2024, the Dark Energy Survey released results from the largest collection of supernova observations ever made from a single study. More than 1,500 stellar deaths, carefully catalogued and analysed. Initially, the data seemed consistent with a constant dark energy, but when researchers combined it with other measurements, something did not quite add up. The data was hinting that dark energy might not be constant after all, that its influence might be changing over time. This was not what anyone expected to find, and the uncertainties in the data were large enough that scientists could not draw firm conclusions. But it was enough to raise the question. And once raised, it demanded a more thorough investigation. For that, astronomers turned to an instrument called DESI, the Dark Energy Spectroscopic Instrument, installed on a 4-meter telescope in Arizona. It is capable of capturing the light of 5,000 galaxies simultaneously. And its mission is precisely this: to measure the expansion history of the universe across billions of years with enough precision to determine whether dark energy is truly constant or whether it has been changing. DESI does this by measuring something called baryon acoustic oscillations. These are essentially the fossilized remnants of sound waves from the very early universe. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma in which sound waves traveled like ripples through a vast cosmic sea. When the universe cooled and became transparent, those sound waves froze in place. They left an imprint in the distribution of matter, a slight preference for galaxies to be separated by a particular distance, like the rings left in a pond after a stone is dropped in. By measuring how this preferred separation has changed across cosmic time, astronomers can trace the expansion history of the universe with extraordinary precision. And because the size of this pattern was set in the early universe and is very well understood, it acts as a kind of cosmic ruler, a fixed measuring stick stretching across billions of light years. In 2025, DESI released results from the first 3 years of its 5-year survey. Using data from nearly 15 million galaxies, it had built the largest 3-dimensional map of the universe ever created. A map so dense with galaxies, each one containing hundreds of billions of stars, that it is genuinely difficult to comprehend. And the results were striking. When the DESI data was combined with observations of the cosmic microwave background, supernova redshifts, and measurements of gravitational lensing, the picture that emerged added significant weight to what the dark energy survey had hinted at the year before. Dark energy's influence appears to be changing, and more specifically, it appears to be decreasing. The best estimates suggest that dark energy's push has weakened by roughly 10% over the last 4.5 billion years. Think of it like a car that is still accelerating, but with a driver whose foot is gently lifting from the gas pedal. The universe is still expanding faster and faster, but the rate at which it is accelerating is itself slowing. If this is confirmed, the implications are significant. A constant dark energy leads to the big freeze, a forever expanding, forever cooling universe. But a weakening dark energy opens the door to something quite different. If dark energy continues to weaken, if it decreases over time and eventually becomes negative, then the expansion of the universe could slow, stop, and reverse. Space, which has been growing for nearly 14 billion years, could begin to contract. Galaxies that have been drifting apart would begin to draw together again. The universe would collapse inward, growing hotter and denser with every passing moment, until everything that exists, every star and galaxy and particle, is compressed back toward a single point in an event called the Big Crunch, the exact opposite of the Big Bang. Whether this will actually happen remains unknown. The current evidence for evolving dark energy is strong, but it has not yet reached the threshold that physicists require to call something a confirmed discovery. On its own, the DESI data sits at just above 2 sigma, which corresponds to roughly 95% confidence. Interesting, but not conclusive. When combined with other data sets, the confidence rises. Some combinations push past 4 sigma, corresponding to more than 99.9% confidence. But the gold standard in physics is 5 sigma, a level at which the probability of the result being a random fluctuation drops to less than 1 in a million. And even 5 sigma results have occasionally turned out to be wrong, as a famous incident at a laboratory in Italy demonstrated in 2011, when physicists reported that neutrinos appeared to be traveling faster than light at a confidence level of 6 sigma, only for the result to later be traced back to a loose fiber optic cable. So caution is warranted. The results are exciting. They are suggestive. They are pointing in a consistent direction, but they are not yet a confirmed discovery. DESI is still running. It is currently in its fourth year of a 5-year survey, and it is expected to eventually measure 50 million galaxies. Alongside it, the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will extend these measurements across even larger volumes of space. And the Vera Rubin Observatory, currently being commissioned in Chile, will scan the sky for millions of supernovae, building the enormous dataset needed to push confidence levels higher. By the end of this decade, we may know whether dark energy is truly constant, or whether the fate of our universe is something other than the long, slow, cold ending we have imagined for 30 years. It is a question worth holding gently as you settle towards sleep. But there is a third puzzle, and in some ways, it is the most quietly unsettling of the three. It is a number, just one number, and it is called the Hubble constant. To understand why this number matters so much, we need to go back even further, back to the very foundations of our understanding of the cosmos. For most of human history, the universe was small, or at least we imagined it was. Ancient civilizations pictured the Earth as flat and covered by a dome of stars. The movements of the sun and moon were mysteries of profound religious significance. By the 2nd century, the astronomer Claudius Ptolemy had developed a model of a geocentric universe, with the Earth fixed at the center and everything else revolving around it. It was a model that would persist, largely unchallenged, for more than 1,000 years. The revolution came slowly. In the 1500s, Nicholas Copernicus proposed that the Earth was not the center, that it was one of several planets orbiting the Sun. A century later, Galileo confirmed it with his telescope. And then, in the 1800s, astronomers began to map the Milky Way itself, revealing it to be a vast disk-shaped system of hundreds of billions of stars. But even then, the question remained. Was the Milky Way the entire universe, or were there other galaxies beyond it? The answer came in 1923, when Edwin Hubble pointed the world's largest telescope at that time, the 100-inch Hooker telescope at the Mount Wilson Observatory in California, at the Andromeda Nebula. Inside it, he found individual stars of a particular type called Cepheid variables, whose brightness pulses in a regular cycle that is directly related to how luminous they actually are. By comparing their true brightness to how dim they appeared, Hubble calculated that Andromeda was some 900,000 light-years away, far too distant to be part of the Milky Way. There was another galaxy out there, and then more. Hubble went on to identify dozens of other galaxies, some as far as 20 million light-years away. The universe was not the Milky Way. The Milky Way was just one of countless island galaxies in an immeasurably larger cosmos. But Hubble's greatest discovery was still to come, working alongside the earlier observations of an astronomer named Vesto Slipher, who had spent years cataloguing the redshifts of distant galaxies. Hubble noticed something remarkable. Not only were galaxies moving away from us, but the farther away they were, the faster they were receding. There was a direct, proportional relationship between a galaxy's distance and its speed of recession. Double the distance, and the galaxy moves away twice as fast. This relationship has one extraordinary implication. It means that space itself is expanding. Not that galaxies are flying through space away from each other, but that the fabric of space between them is stretching. Every point in the universe is moving away from every other point, not because of any explosion or force, but because space itself is growing larger. Hubble announced this finding in 1929. It was the observational confirmation of what the Belgian physicist Georges Lemaitre had proposed theoretically 2 years earlier. The universe was expanding, and if you ran that expansion backward in time, everything would have once been together, compressed into an inconceivably small and dense state. A beginning, what would come to be known as the Big Bang. The rate of this expansion, the relationship between a galaxy's distance and its speed of recession, became known as the Hubble constant, usually written as h0 and measured in kilometers per second per megaparsec, a megaparsec being about 3.3 million light years. Hubble's original estimate was quite high, about 500 kilometers per second per megaparsec. Over the following decades, as measurements improved, the value was revised downward substantially. Today, most estimates place it somewhere in the range of 65 to 75 kilometers per second per megaparsec. But here is the problem. There are two fundamentally different ways to measure the Hubble constant, and they give different answers. The first method is called the cosmic distance ladder. It measures the expansion of the universe as we observe it today, in the present or recent universe. It works by building up a chain of distance measurements. First, you calibrate distances to nearby stars using parallax, the slight shift in a star's apparent position as the Earth moves around the Sun. Then, you use those measurements to calibrate the distances to Cepheid variable stars in nearby galaxies. Then, you use those to calibrate the brightness of Type 1a supernovae. And then, you use supernovae to measure distances across enormous cosmic scales. At each step, you refine and extend your reach. And when you put it all together and calculate the Hubble constant, you get a value of approximately 73 to 76 kilometers per second per megaparsec. The second method works in the opposite direction. Instead of measuring the expansion as we see it now, it estimates what the expansion rate should be today by starting from the very beginning. It uses the cosmic microwave background, that ancient snapshot of the universe from 380,000 years after the Big Bang, and it runs the physics of the universe forward in time using the standard cosmological model. Given what we know about how much dark matter and ordinary matter and dark energy exist, and given the initial conditions imprinted in the microwave background, what Hubble constant does the model predict? The answer, from the Planck satellite's extraordinarily detailed measurements of the cosmic microwave background, is approximately 67.4 kilometers per second per megaparsec. Two methods, two answers, a difference of somewhere between 6 and 9 kilometers per second per megaparsec, depending on which measurements you use. It sounds small, but in cosmological terms, it is enormous. The error bars on each measurement have shrunk over the years as techniques have improved, and the two values have not converged. If anything, the gap between them has grown more pronounced. This discrepancy has become known as the Hubble tension, and it matters enormously. The Hubble constant is not just a number, it is a foundation. It determines the age of the universe. It determines the size of the observable cosmos. It feeds into calculations about the growth of structure over time, the formation of the first galaxies, the distribution of dark matter, the behavior of dark energy. If the Hubble constant is wrong, or if the two measurements are revealing a genuine gap in our understanding, then the entire standard model of cosmology may need to be revised. Several independent measurements have been made using entirely different techniques, all trying to settle the question. Astronomers have used megamassa hosting galaxies. These are galaxies that contain certain molecules, like water vapor near a central supermassive black hole. These molecules can amplify microwave radiation, creating a maser, which is like a laser, but for microwaves. By mapping the rotation and position of these masses with great precision, astronomers can measure the distance to their host galaxies with extraordinary accuracy and calculate the Hubble constant without relying on the usual chain of calibrations. A 2020 study using this method found a value of around 73.9 kilometers per second per megaparsec. Another independent measurement in late 2024 using data from the Dark Energy Spectroscopic Instrument to study 12 Type 1a supernovae in the Coma galaxy cluster found a Hubble constant of 76.5. And in 2025, researchers in India used a different class of pulsating star called Mira variables to anchor distances to faraway galaxies, arriving at a value of 73. All of these measurements using the present universe method cluster around 73 to 76. All of them fall comfortably outside the error range of the early universe methods, 67.4. The gap will not close. One leading astronomer involved in the DESI supernova study, a professor of physics at Duke University, has said that our model of cosmology might be broken, and that the Hubble tension is beginning to feel less like a tension and more like a crisis. Without resolution, the model we use to interpret everything from galaxy formation to the cosmic future rests on uncertain foundations. So what could explain it? Several possibilities have been proposed. One is that there is something we are missing in the early universe, some process or particle that affected how the universe evolved in its first few 100,000 years, in a way that is not captured by our current model. If the early universe expanded slightly differently than we think, the Hubble constant, inferred from the cosmic microwave background, would shift. Another possibility is that dark energy is not constant, that it has changed over time. This connects back to what DESI has been finding. If dark energy was stronger in the early universe than it is today, it could have altered the expansion history in a way that pushes the two Hubble constant measurements apart. There is also the possibility that dark matter is not quite what we think it is. Some theorists have suggested that dark matter particles might slowly decay over time, subtly changing the gravitational landscape of the cosmos. And then there is the most intriguing recent proposal. A paper published in 2025 suggested that the Hubble tension might be resolved if the universe has a very slow rotation. Not any one part of it, the entire universe. Spinning once every 500 billion years. So slow as to be completely undetectable by any current measurement, but just significant enough to affect the expansion history of the cosmos in a subtle way. The paper's authors showed that when this slow spin is introduced into the equations, the model predicts an early universe with a lower rate of expansion, consistent with the microwave background measurements, and a present universe with a higher rate, consistent with the redshift measurements. Both values, in other words, could be correct. They could simply be measuring the expansion at different points in a universe that is not expanding at exactly the same rate in all directions, because it is slowly rotating. One of the paper's authors, from the University of Hawaii, paraphrased the ancient Greek philosopher Heraclitus when describing the hypothesis. Panta rei, he said, everything flows, everything moves, everything perhaps, even the universe itself. It is an idea that is still in its earliest stages. The authors were careful to describe it as a preliminary calculation. Much more work would need to be done to test it against the full range of cosmological observations. But it is a beautiful idea, It does not violate any known laws of physics. And there is something quietly wonderful about the thought that just as our planet spins and our solar system orbits and our galaxy rotates around its supermassive center, the universe itself might be turning, imperceptibly slowly, in the dark. So we have arrived at a particular moment in the history of astronomy, a moment in which three great puzzles are coming into focus at the same time. The missing matter of the universe. 40% of all ordinary baryonic matter may have been hiding in the vast hot filaments of the cosmic web. The first clear X-ray image of one of those filaments, stretching 23 million light-years between galaxy clusters, has just been captured, and the Euclid Space Telescope, currently mapping the cosmos with extraordinary precision, may by 2030 have gathered enough data to confirm whether the cosmic web we observe matches the predictions of the Big Bang model. If it does, it will be one of the strongest confirmations of our standard cosmological model in history. Dark energy, the force responsible for the accelerating expansion of the universe, may not be the fixed constant our models have assumed. It may be weakening. And if it continues to weaken, the long-predicted big freeze may give way to something entirely different. A reversal, a collapse, a big crunch. Instruments like DESI, Euclid, the Nancy Grace Roman Space Telescope, and the Vera Rubin Observatory are all working toward the measurements that will tell us whether this is truly happening. And the Hubble constant, that single foundational number that underpins so much of our understanding of the cosmos, refuses to resolve. Two methods, two answers. A gap that has not narrowed despite decades of increasingly precise measurement. Something in our model of the universe is either incomplete or incorrect, and discovering what that something is may require revising our understanding not just of dark matter or dark energy, but perhaps of gravity itself. These are not small questions. They are the largest questions that human beings have ever asked. And they are being asked by thousands of astronomers and physicists and cosmologists, working with telescopes scattered across the surface of the Earth and floating in the cold of space, analyzing data from billions of galaxies, refining calculations, checking and rechecking and checking again. It is slow work, patient work, the kind of work that unfolds over years and decades and sometimes generations. The kind of work that requires holding a question carefully, without rushing toward an answer, trusting that the universe will eventually reveal itself. There is something in that kind of patience that feels right for a night like this one. The universe is old, incomprehensibly, unimaginably old. 13.8 billion years is a duration that no human nervous system can truly feel. We can say the words, we can write down the number, but the actual passage of that much time, the slow cooling of that first hot brightness into stars, and then into galaxies, and then into the vast, quiet, structured cosmos we observe today, that is something that can only be approached obliquely, in the dark, in stillness. When the mind has let go of its ordinary preoccupations, what we know is this. 14 billion years ago, everything that exists was compressed into something unimaginably small and hot. And then it expanded. And as it expanded, it cooled. And as it cooled, the first particles formed, and then the first atoms. And then gravity began its slow, patient work of drawing matter together. The first stars ignited, burning brilliantly for a few million years, and then dying in enormous explosions that seeded the cosmos with heavier elements. Carbon, oxygen, iron, the building blocks of everything that would come after. Over billions of years, those elements gathered into new stars and new solar systems. planets formed, and on at least one of them, in conditions that we still do not fully understand, something extraordinary happened. Chemistry became biology, and billions of years after that, biology became curiosity. We are made of the matter that has been here since the beginning. The iron in your blood was forged in a dying star. The calcium in your bones was scattered across space in a supernova. The water in your body carries hydrogen atoms that have existed since the first few minutes after the Big Bang. You are, in the most literal sense, a part of the universe that has folded back upon itself and learned to wonder about its own origins. And right now, in laboratories and observatories around the world, other parts of the universe, other collections of ancient atoms arranged into curious, wondering minds, are working patiently on the questions we have been sitting with tonight. Where is the missing matter? What is dark energy really? Why does the universe seem to be expanding at two different rates, depending on how you measure it? They do not yet have complete answers, but they are closer than they have ever been. And the questions themselves, the asking, the looking, the patient accumulation of careful observation, that is its own kind of remarkable thing. The universe has been here for nearly 14 billion years. It will be here for trillions more, regardless of whether it ends in a freeze or a crunch or something we have not yet imagined. Our window of looking is brief. A few centuries of telescopes, a few decades of space observatories, a few years of DESI and Euclid and Roman and Rubin. But in that brief window, we have learned more about the cosmos than in all the rest of human history combined. We have mapped the structure of the universe on scales of hundreds of millions of light years. We have imaged the ancient light from 380,000 years after the beginning of time. We have detected the gravitational ripples from colliding black holes. We have photographed the shadows of supermassive black holes in the centers of galaxies. And now, at last, we have captured the faint X-ray glow of the cosmic web's own filaments. We are finding the hidden things, slowly, one by one. And that, perhaps, is the most comforting thought of all to carry into sleep. Not that we have the answers, but that we are asking the right questions, that the universe, for all its scale and strangeness and mystery, is not beyond the reach of patient human curiosity. The filaments of the cosmic web stretch silently between the galaxy clusters tonight, 23 million light-years long, glowing faintly in X-rays that no human eye will ever see directly, but that our instruments have learned to read. The universe is expanding, still, in every direction at once. And somewhere out there, in the deep data of DESY's galaxy maps, the answer to whether dark energy is truly constant or slowly fading may already be hidden, waiting for someone to look carefully enough to find it. There is no rush. The cosmos has been patient for 14 billion years. And so, tonight, can we? Let the questions settle around you like the dark between stars. Let the scale of things, that immense, quiet, unhurried scale, do what it always does when you give it enough space. Let it make the small worries small. Let it make the breath come slower. Let it remind you that you are here, briefly, in the middle of an unimaginably large and beautiful mystery. And that is more than enough.